Welcome aboard, explorers! You've just entered BrightBoundX, where we break down the cosmos, not as it appears in science fiction, but as it actually unfolds in the mathematics of motion, the constraints of physics, and the ingenuity of human engineering. Today, we're answering a question that has captivated humanity for generations. If we can reach the moon in 3 days, why does it take months or even years to reach our planetary neighbors? Here's the catch. The answer isn't what you expect. It's not about distance alone. It's about energy, orbital mechanics, and the brutal physics of acceleration and deceleration in the vacuum of space. By the end of this exploration, you'll understand why a journey to Mars takes 9 months, why Saturn demands 6 years or more, and why Neptune remains humanity's final frontier destination that would consume nearly 3 decades of human life in transit. The question isn't just about time. The real question is, what is humanity willing to sacrifice to touch the stars? Before we embark on our journey to distant worlds, we must dismantle a fundamental misconception about space travel. Most people imagine spacecraft launching directly toward their targets, following straight lines through the void. This is profoundly incorrect. Planets don't maintain fixed positions in space. They exist in constant motion, orbiting the Sun along elliptical paths at varying speeds. Mercury races through its orbit faster than Jupiter, which grows at a leisurely pace in the outer reaches. A planet's position today tells you nothing about where it will be in 6 months. Perihelion and aphelion, the dance of distance. Each planet traces an ellipse, not a circle. At perihelion, the planet reaches its closest point to the Sun. At aphelion, it stretches to its farthest distance. This seemingly simple fact creates an astronomical complication. There is no single, fixed distance between Earth and any other planet. Take Mercury, for example. At its closest approach inferior conjunction, it orbits just tens of millions of miles from Earth. At its most distant, the gap widens dramatically. Mercury possesses the most eccentric orbit in our solar system, a measurement of 0.1, meaning its path deviates significantly from circular. Venus, by contrast, orbits with an eccentricity of 0.06, maintaining a much more regular distance. This orbital variability transforms the simple question how long to reach Mercury into a complex calculation of variables, launch windows, and optimal trajectories. The problem of the moving target. Imagine coordinating a meeting when your partner is constantly moving. You can't simply head in their direction. Instead, you must anticipate where they'll be when you arrive. In spaceflight, this prediction becomes a physics ballet, a choreography of launch timing, trajectory angles, and acceleration profiles. Pointing a rocket directly at a planet and hitting the button is futile. By the time your spacecraft arrives, the planet has shifted position. Engineers must calculate the precise moment of launch to ensure that the spacecraft's path intersects with the planet's future location at the exact moment of arrival. Hohmann transfer, the elegant solution. The most fuel-efficient method known to space engineers is the Hohmann transfer, an elliptical orbit that departs from Earth and kisses the target planet's orbit. A single, carefully timed acceleration sends the spacecraft on a path that requires minimal fuel expenditure. For Mars, these optimal Hohmann windows open only every 26 months. Miss one, and you wait more than 2 years for the next opportunity. This constraint alone explains why Mars missions, despite their obvious appeal, arrive so infrequently. The trade-off is time. Efficiency demands patience. A fast, direct approach to Mars would burn enormous quantities of fuel, reduce payload capacity, and consume precious resources for a mere matter of weeks, say. Engineers choose the slow path, and humanity's deep space missions grow measured in seasons, not days. Mercury beckons with mysteries. As the smallest planet and closest to the Sun, it serves as a cosmic window into the formation and evolution of our solar system. Yet reaching this scorched world demands extraordinary precision. Why Mercury matters? Mercury's surface bears the scars of ancient volcanism. Its metallic core generates a surprisingly robust magnetic field for such a diminutive world. Beneath the cratered surface lies evidence of processes that shape every planet orbiting our star. Scientists hypothesize that even water may have existed on Mercury in its ancient past, opening the tantalizing possibility that habitable conditions, however briefly, may have graced this infertile world. To understand Mercury is to understand planetary birth itself. The challenge of proximity. Here's the paradox. Mercury's closeness to the Sun, the very feature that makes it scientifically valuable, becomes its greatest obstacle. The Parker Solar Probe has achieved speeds exceeding 690 to 1,000 kilometers per hour for 130,000 miles per hour. Even at such extraordinary velocity, reaching Mercury demands more than 4 months. Why? Because speed alone accomplishes nothing without deceleration. To enter orbit around Mercury, a spacecraft must slow dramatically relative to the planet. The Sun's gravity well near Mercury creates a ferocious environment. Conventional atmospheric braking using a planet's atmosphere to dissipate velocity is impossible. Mercury possesses virtually no atmosphere to harness. Instead, deceleration relies almost entirely on engine burns, consuming vast quantities of fuel. Historical lesson in orbital patience. Mariner 10, launched in 1973, demonstrated the necessity of gravity assists. By utilizing Venus as a gravitational springboard, Mariner 10 reached Mercury in approximately 6 months, delivering humanity's first close-up images of this enigmatic world. Decades later, Messenger 2004 executed an intricate ballet of gravitational assists coordinating with Earth, Venus, and finally Mercury itself over 6.5 years of travel before entering orbit. 4 additional years of study followed before fuel depletion ended the mission. Today, the P. Columba, launched in 2018 by the ESA and JAXA partnership, employs solar electric propulsion combined with multiple gravity assists. This patient approach extends the journey, but optimizes fuel consumption for sustained scientific investigation. The pattern is unmistakable. To stay requires time. 2+ demands energy efficiency, not speed. A 4-month transit to Mercury represents not laziness, but practical optimization. The minimum time required to arrive at a velocity low enough for orbital capture without expending an impossible quantity of propellant. Venus shines as the brightest object in our night sky after the Sun and Moon. Ancient astronomers called it the morning star, the evening star, a beacon of beauty. Our planet transformed. Venus was not always this way. Billions of years ago, it may have harbored conditions favorable to life: liquid water, moderate temperatures, perhaps even oceans. A runaway greenhouse effect transformed this habitable world into a pressure cooker, evaporating the oceans and baking the surface into a geological hellscape. Understanding this catastrophic transformation may illuminate the fate of other planets, including the potential future of Earth itself. The geometry of arrival. Venus maintains the most circular orbit among the terrestrial planets and eccentricity of 0.06, making its behavior relatively predictable compared to Mercury's erratic path. Yet prediction remains complex. At inferior conjunction, when Earth and Venus align on the same side of the Sun, the distance shrinks to its minimum. Every 8.48 years, Earth and Venus return to nearly the same relative positions, creating a rhythm to interplanetary missions. At closest approach, the distance may be merely 38 million kilometers. At greatest separation, it expands to 259 million kilometers. These variations fundamentally alter transit calculations. The historical record, The Soviet Union's Voyager 1 in 1961 pioneered Venus exploration, though it lost contact after 97 days, passing approximately 100,000 kilometers from the planet without direct observation. Mariner 2 achieved the first successful flyby in 1962, completing its journey in 110 days, a record that stands as one of the fastest interplanetary transits ever accomplished. The SAS Venus Express traveled for 153 days. The variation reflects a fundamental truth. Flyby missions can sprint, orbital missions must follow. The economics of efficiency. On average, successful Venus missions occupy 120 to 180 days of transit. Theoretical optimization with advanced engines might reduce this to 60 to 80 days. But such aggressive trajectories demand fuel reserves that current technology can barely provide. Surface exploration compounds the challenge. The legendary Voyager 9 and Voyager 10 landers survived the harsh environment for nearly 53 and 65 minutes respectively before succumbing to thermal and chemical destruction. The planet's surface remains largely unmapped, photographed only by these brief Soviet heroics. Venus teaches a harsh lesson. Proximity does not guarantee accessibility. The brightest beacon in the sky remains largely beyond our grasp. Mars occupies a unique position in human imagination. Unlike Mercury's extreme proximity or Venus's hostile atmosphere, Mars presents itself as approximately habitable a world where humans might someday walk beneath alien skies. The journey to Mars has been blazed in both cooperation and competition. NASA emphasizes safety through redundancy and testing. SpaceX pursues aggressive timelines and bold technological leaps. Paradoxically, these apparently opposed philosophies may ultimately complement each other, accelerating humanity's departure from Earth. The variable distance problem. In 2003, Earth and Mars achieved one of their closest approaches in recorded history, approximately 56 million kilometers. In other configurations, the planets separate to more than double that distance. This variation transforms Mars from a nearby destination to a remote outpost, depending upon launch timing. If we consider light speed travel as a theoretical reference, communication with Mars varies from approximately 3 minutes at closest approach to more than 20 minutes at greatest separation. For actual spacecraft, the mathematics prove far more complex. New Horizons, traveling toward Pluto at approximately 58,000 kilometers per hour, could theoretically reach Mars in 160 days at average distance, 389 days in worst-case scenarios, and as little as 39 days during exceptionally favorable alignment. The Parker Solar Probe's peak velocity would reduce this to mere hours in the most optimistic theoretical scenario. Yet these figures represent pure thought experiments disconnected from reality. The Hohmann transfer equation. Real missions employ the Hohmann transfer, an elliptical path departing Earth orbit and touching Mars's orbit. This elegant solution minimizes fuel consumption but demands patience. A complete cycle launch, transit, orbital insertion, and stay consumes approximately 26 months. Typical missions occupy 9 months in transit. A complete round-trip mission including landing, surface operations, and return may consume up to 21 months. This extended duration reflects not technological limitation, but the physics of efficient spaceflight. The Starship revolution. Traditional spacecraft operated under severe constraints. Heavy shielding, limited payload, and expendable design meant each mission consumed enormous resources for a single journey. SpaceX's Raptor engines and Starship architecture introduced reusability and dramatic payload capacity. If these technologies deliver their promise, Mars transitions from an expedition requiring extraordinary resources to a destination of routine though still challenging accessibility. Travel time becomes secondary to frequency. How often can we go? On what schedule? the question shifts from when will we arrive to when will we depart. Human factors. A 9-month journey through space demands extraordinary psychological resilience. Crews remain confined in tight quarters, watching Earth shrink to a pale dot in the window. Radiation exposure, muscle atrophy, bone density loss, and psychological strain accumulate relentlessly. Yet Mars calls to us. The possibility of another world. The potential for extraterrestrial life in past or present form. The human imperative to expand beyond our planetary cradle. These motivations overcome the hardships of the journey. Jupiter represents a threshold. The terrestrial planets Mercury, Venus, Mars remain within the Sun's inner domain. Jupiter initiates entry to the realm of giant planets, a domain of staggering scale and complexity. This solar system's largest world is a living laboratory. Continent-scale storms persist for centuries. A colossal magnetic field dwarfs Earth's by orders of magnitude. An entire moon system Europa, Ganymede, Callisto, and dozens of smaller companions orbit this giant like a miniature solar system unto itself. The promise of the moons. Jupiter's major moons may harbor conditions favorable to life. Europa's frozen surface conceals what scientists believe to be a global ocean of liquid water beneath the ice, potentially harboring microbial life. Ganymede, the largest moon in our solar system, possesses its own magnetic field, suggesting internal geological activity. Callisto's ancient, heavily cratered surface preserves a record of the early solar system. In many ways, the Jupiter system may offer superior prospects for discovering extraterrestrial life compared to Mars. The distance calculation. Jupiter's distance varies dramatically. At optimal alignment, approximately 365 million miles separate Earth from Jupiter. In worst-case scenarios, this expands to nearly 600 million miles. Average separation hovers around 483 million miles a distance, so vast that a hypothetical automobile traveling at 110 kilometers per hour would require centuries to cross. Historical transit times. Pioneer 10, the first spacecraft to reach Jupiter, completed its journey in approximately 640 days at the red route that bypassed orbital insertion in favor of a gravity-assist slingshot toward the outer planets. Pioneer 11 and the Voyager spacecraft followed similar high-speed trajectories, passing Jupiter to accelerate toward even more distant destinations. Galileo, by contrast, pursued a patient approach. This orbiter required nearly 6 years to reach Jupiter, employing Venus-Earth gravity assists, legal trajectory to arrive at the precise velocity necessary for orbital capture. The extended journey permitted sustained scientific observation impossible during brief flybys. In 2006, New Horizons set a record for Jupiter transit speed approximately 405 days while using the giant planet's gravity to accelerate an additional 8,700 miles per hour toward Pluto. The human challenge, transporting humans to Jupiter and back, represents an extraordinary logistical undertaking. For a crew of 4, basic nutrition alone demands approximately 8,000 pounds per year, totaling 48,000 pounds for the outbound journey not including return supplies. Add water, oxygen generation systems, radiation shielding, redundant electronics, medical facilities, and waste recycling systems, and the mass requirements become staggering. Protection against energetic solar particles and cosmic radiation demands shielding mass the current spacecraft simply cannot accommodate. Psychological effects of confinement compound these physical challenges. 6 years of travel through emptiness, Earth visible only as a pale point of light, test human resilience in ways terrestrial experience cannot prepare. Generalized orbital mechanics suggest that an efficient trajectory to Jupiter orbit requires nearly 6 years. Add to this the gravity assists, orbital insertion burns, and mission operations, and realistic human missions might consume 7 to 8 years simply in transit. Current and upcoming missions. NASA's Europa Clipper launched with arrival plan for 2031. will conduct extensive surveys of Europa's surface without landing. ESA's JUICE mission will arrive around 2029, dedicated to touring the Jovian main system. Both missions employ extended trajectories to enter orbit safely. Both prioritize science over speed. The pattern remains constant. To stay requires patience. To observe demands time. Saturn has captivated human imagination since Galileo first glimpsed its rings through a primitive telescope. These magnificent structures composed of countless particles of ice and rock pose questions that contemporary science has only begun to answer. How did these rings form? Why the colors vary? Why does Saturn emit more heat than it receives from the Sun? Beyond the rings orbit the moons, Titan, cloaked in a thick atmosphere and covered in seas of liquid methane, represents perhaps the most exotic world in our solar system. Enceladus vents plumes of salty water into space, suggesting a global subsurface ocean. Yet Saturn remains among the most distant destinations humanity has explored. The journey to Saturn's distance oscillates between approximately 1.2 billion kilometers at closest approach, and more than 1.7 billion kilometers at greatest separation. At average distance, Saturn orbits roughly 1.4 billion kilometers away. The spacecraft that revolutionized our understanding of Saturn Cassini did not travel directly. Instead, it executed a complex gravity assist ballet. To Venus flybys, a return to Earth, a Jupiter gravity assist, and only then did the orbiter approach Saturn, arriving after 7 years of travel. Pioneer 11, benefiting from an excellent planetary alignment, required more than 6 years. Voyager 1, in an exceptionally favorable configuration, completed its transit in approximately 3 years and 2 months, a record that reflects exceptional orbital geometry rather than superior technology. Cassini consumed 7 years reaching Saturn, having optimized its trajectory for safe orbital insertion and sustained scientific operations. New Horizons set a speed record during its Saturn passage approximately 2 years and 4 months, but continued onward, utilizing Saturn's gravity to accelerate toward the outer planets. The trade-off between speed and efficiency. The variation in transit times reflects a consistent principle. Route selection, number of gravity assists, and engine power determine arrival time. Critically, a spacecraft intended for orbital operations must arrive at reduced velocity relative to Saturn. A probe passing through space at 15 kilometers per second cannot simply maintain that speed at Saturn's location. The planet's gravity will accelerate it further. To enter orbit safely, engineers must reduce velocity through prolonged engine burns, weeks or months of deceleration to safely match Saturn's orbital speed of approximately 9.7 kilometers per second. Human missions, the distant dream. A crewed mission to Saturn represents ambitions at the very edge of current technological possibility. Conservative estimates suggest an 8-year outbound journey. Life support systems, radiation shielding, redundant safety systems, and provisioning for a crew of 4 will transform the spacecraft into a propellant skyscraper. The return journey compounds the challenge. Ideally, a spacecraft would use Jupiter as a gravity assist slingshot homeward, but only if Jupiter happens to be favorably positioned at the precise moment of departure. Achieving this requires extraordinary planning, determining Saturn arrival date, operational duration, and departure window in coordination with Jupiter's orbital mechanics. More realistically, a human Saturn mission might consume 12 to 15 years total mission duration, 8 years outbound, 2 to 4 years in Saturn orbit, and 4 to 6 years returning. A lifetime commitment for a select few explorers. Scientific priorities. In contrast to human exploration, robotic missions to Saturn offer practical advantages. Cassini's 13-year orbital tour generated an encyclopedia of Saturn knowledge. Future missions will expand this understanding, revealing secrets of the rings, the moons, and the planet's extraordinary internal dynamics. The logical path forward remains robotic exploration, learning systematically through each mission and incrementally advancing human capabilities and knowledge. Beyond Saturn's rings lie the ice giant Uranus and Neptune, worlds so distant that sunlight requires more than 2 hours to reach them. These bluish spheres present deceptive similarity, masking fundamental differences. The chemistry of blue. The blue hue of these worlds does not indicate oceans. Rather, an atmosphere of hydrogen and helium infused with methane, ammonia, water, and hydrogen sulfide absorbs red wavelengths and reflects blue. This chemistry creates visual similarity, concealing radically different worlds beneath. Uranus, the oddity. Uranus spins on its side, its axis tilted approximately 98 degrees, an extreme inclination that suggests a catastrophic collision in the ancient past. Its magnetic field, misaligned by nearly 60 degrees and offset from the planetary center, further indicates internal chaos. Voyager 2's 1986 encounter revealed Uranus as an almost serene disk lacking obvious storms or dynamic features. Infrared telescopes later revealed this apparent calm as deceptive. Uranus remains active, though less turbulent than its neighbor Neptune. Photochemical haze mutes surface contrast, creating a washed-out appearance contrasting with Neptune's vivid visual presentation. Neptune, pure dynamism. Neptune seethes with activity. Winds exceed 1,700 kilometers per hour, among the fastest in the solar system. Great dark spots appear and vanish. The atmosphere churns with dynamic complexity, preventing the photochemical haze formation that mutes Uranus's features. The moons tell equally fascinating stories. Uranus's 5 largest moons, Miranda, Ariel, Umbriel, Titania, and the Oberon, display young geological surfaces dominated by giant scarps. Miranda may feature a freefall distance exceeding 20 kilometers across its icy crust, suggesting collisional reassembly in the ancient past. The scientific imperative, understanding our ice giants, illuminates exoplanetary science. Ice giant planets are common around distant stars. Comprehending Uranus and Neptune provides crucial insights into planetary system formation throughout the galaxy. Uranus, the future mission. The scientific community has prioritized the Uranus orbiter and probe mission, a dedicated spacecraft combining an orbiter for extended observation and an atmospheric probe for direct atmospheric analysis. The most favorable launch windows cluster around mid-2031 through 2032, utilizing Jupiter for gravitational assistance. Cruise time to Uranus spans approximately 13 years. Alternative launch windows available in subsequent years would require circuitous inner-planet gravity assist sequences, extending travel beyond 15 years. The investment demands billions of dollars and 2 decades of waiting. Yet the scientific return justifies every expense. Fundamental knowledge of how planetary systems form, evolve, and sustain complexity. Neptune, the lonely sentinel. Neptune remains humanity's least explored planet. Only once has a spacecraft visited this distant world, Voyager, to achieve the so close encounter in 1989. And only because of a rare celestial alignment that repeats every 176 years. The Great Alignment of 1977-1989. In the 1970s, an extraordinary planetary alignment aligned Jupiter, Saturn, Uranus, and Neptune in a configuration permitting a single spacecraft to visit all 4 giants sequentially. Voyager to exploit this alignment, using successive gravity assists from each planet to accelerate toward the next. The probe jumped from Jupiter to Saturn to Uranus to Neptune, accumulating speed from each gravitational encounter. This gravity assist ramp enabled exploration impossible through conventional means. Without these assists, reaching Neptune would have consumed 5 times as much fuel. This alignment will not recur for another 176 years. For contemporary mission planners, the 1977 to 1989 alignment represents a once-in-human history opportunity used beautifully, but never to be repeated by current generation humanity. The deceleration problem. Neptune's distance from the Sun means the planet orbits at only 5.4 kilometers per second. Voyager 2, stacking assists, approached Neptune at approximately 15.5 kilometers per second, nearly 3 times faster. Capturing a spacecraft in orbit at such velocity requires extraordinary measures. The probe must decelerate through prolonged engine burns. For a craft the size of Voyager, the fuel required for such deceleration exceeds the spacecraft's own mass by a factor of 10 or more. A human mission compounds this challenge enormously. A heavy spacecraft carrying life support systems, radiation shielding, and supplies cannot rely on brief engine burns. Deceleration must occur gradually to avoid subjecting astronauts to excessive forces. The braking period could stretch from 2 months for a lightweight probe, 2 years for a human-rated spacecraft. Add this deceleration time to the cruise duration, and the human Neptune mission consumes 24 to 28 years simply reaching orbit. The return journey consumes similar duration, or longer. With current chemical rocket technology, a round-trip human mission to Neptune demands fuel reserves of such magnitude that the spacecraft would be more than 90% propellant hard. The absolute edge of technological possibility, and perhaps beyond current capability. Pluto, reclassified as a dwarf planet in 2006, retains a place in human imagination disproportionate to its size. This distant, icy wall circles the Sun on an eccentric orbit, sometimes approaching 30 astronomical units from our star, other times stretching to 50 astronomical units. 1 equals the Earth-Sun distance, approximately 150 million kilometers. A 30 astronomical unit separation means Pluto sometimes orbits 4.5 billion kilometers away. At 50 astronomical units, the distance extends to 7.5 billion kilometers. Communication across such distances requires extraordinary patience. Radio signals traveling at light speed require 4 to 7 hours one way. A command sent from Earth takes many hours to reach Pluto. The reply requires equal time returning. New Horizons, humanity's fastest messenger. New Horizons, launched toward Pluto, represents humanity's boldest venture into the outer solar system. This spacecraft accelerated to approximately 16 kilometers per second, among the fastest speeds any human-made object has achieved. Even at this extraordinary velocity, New Horizons required 9.5 years to reach Pluto. Upon arrival in 2015, it conducted a brief flyby, capturing the first close-up images of Pluto's frozen heart, mountains of water ice, vast plains of nitrogen frost, and a surprising diversity of geological features. The challenge of human exploration. A human mission to Pluto represents ambitions at the absolute extreme of possibility. A conventionally propelled spacecraft would require approximately 35 years to make the journey. 2 generations of astronauts would take turns gazing from the portholes as the Sun shrank to just another bright star in the firmament. Psychological challenges would dwarf the physical hardships. The longest human space mission yet conducted ISS long-duration spaceflight spans mere months. A 3-decade mission approaches the limiting lifetime of human biological systems. Yet perhaps future generations, with propulsion technologies beyond our current comprehension, will accept such challenges. Perhaps the explorers of the 22nd century will view a 35-year mission to Pluto as routine, just as we regard a 9-month Mars journey as ambitious, but achievable. The fundamental lesson: energy, not distance. Throughout this exploration, a consistent principle emerges. Distance is not the primary constraint. Energy is. Changing orbits requires changing velocity. Each additional kilometer per second of velocity change demands exponential fuel expenditure. The spacecraft must not merely reach its destination. It must arrive at precisely the correct velocity for the intended operation. Slower for orbit, faster for flybys, moderate speeds for atmospheric entry. This energy requirement explains the otherwise puzzling variations in transit times. For months to Mercury with orbital capture, 110 to 200 days to Venus, depending on flyby or orbit, 9 months to Mars with Hohmann transfer, 1 year or more to Jupiter with orbital insertion, nearly 6 years to Jupiter orbit if orbital capture required, 4 to 7 years to Saturn depending on trajectory, more than a decade to Uranus, 13 to 15 years to Neptune, 35 years to Pluto, human crewed hypothetically. These times are not arbitrary. They represent the optimization between fuel consumption and mission duration, the physics-based sweet spot, where resources and time balance against scientific routine. Contemporary technology relies on chemical rockets, gravity assists, and patience. Yet engineers and scientists envision alternatives. Solar electric propulsion generates continuous, modest thrust from solar energy. Though acceleration remains minimal, sustained application over months accelerates spacecraft gradually, ultimately achieving high velocities with minimal fuel. Solar sails harness the gentle pressure of photons, providing steady acceleration without any onboard propellant consumption. Unlike engines that require fuel, solar sails operate indefinitely as long as solar radiation reaches them. Nuclear reactors could generate electricity for ion engines, producing continuous thrust far exceeding chemical rockets per unit mass of propellant. Next-generation ion engines promise dramatic improvements in efficiency and thrust. Laser sails could accelerate spacecraft to extreme velocities through ground-based or space-based laser arrays. Each technology addresses a piece of the puzzle. Some reduce cruise time, others minimize required fuel mass. Collectively, they suggest that the journey times we view today may dramatically compress in coming decades. The pattern that brought us here from the first close approach to Mercury, through the Venera heroics, the Mars rovers turning pages of history, Juno diving through Jupiter's magnetic field lines, Cassini's long orbital opera among Saturn's rings, the solitary encounter with Neptune, and the New Horizons revelation of Pluto continues onward. The solar system awaits systematic, methodical, ambitious exploration. Each mission contributes lessons. Each success enables the next adventure. The question how long does it take to reach the planets is less about stopwatch measurements than about understanding how the solar system functions. It's about comprehending the interplay of gravity, orbital mechanics, and the stubborn determination of humanity to navigate this cosmic dance. Distance means nothing without context. Energy, mathematics, and ingenuity transform what appears impossible into the merely difficult. Every minute spent traveling through space repays itself in centuries of accumulated knowledge when the data returns. Here's my challenge to you. If you could select a single destination for close-up exploration, the shadow of a Saturn ring crossing the atmosphere, the fractured ice of Europa harboring a hidden ocean, the calm mystery of Uranus, the dynamic storms of Neptune, or the frozen mystery of Pluto, which would you choose? Where would you place your stamp in the cosmic passport of human exploration? Thank you for joining BrightBoundX on this journey through the solar system. If this exploration expanded your perspective on space, planetary science, or the future of human exploration, I invite you to like this video to support our mission of bringing sophisticated science to a global audience. Subscribe to BrightBoundX and enable notifications so you never miss our deep dives into the cosmos, cutting-edge science, and the wonders awaiting us beyond Earth. Share this with fellow explorers, friends, family, colleagues, anyone curious about humanity's place in the universe. The cosmos is vast, the questions are profound, and the future is unwritten. At BrightBoundX, we explore what's possible when human curiosity meets scientific rigor. See you in the next exploration. BrightBoundX, where curiosity meets the cosmos.